This lecture is on reaction mechanisms, which is simply the step-by-step process by which chemical reactions occur. And most of the time you're just given an overall reaction, like A plus B yields C. But in most cases, what really happens is the reactants go through one or more steps to arrive at the final product C. All right, so we call the individual steps that make up the mechanism for an overall reaction, we call them elementary steps. And there are a couple of requirements for elementary steps. One is that all of the elementary steps must add up to give the overall balanced equation. So just like in Hess's law, if you remember that, when you add reactions up, it's very easy. You just add all of the reactants together, kind of like you're making a new reaction, but make sure you add every single reactant, okay? And then draw your arrow and then go ahead and list every single product. All right? And so then what you do is you cross out what's the same on both sides. So we have C on both sides, we have D on both sides. And so what we end up with is 2A plus B gives E plus F, which is good. So that means that these elementary steps support this overall reaction, and so far they could actually be the mechanism. All right, so when you add elementary steps to give an overall reaction, there are a couple of species that you need to be aware of, and one of them is an intermediate. An intermediate is a substance that is created during the reaction and consumed during the reaction. So it does not show up in the beginning or the end, does not show up as reactants or final products. So if you look at the elementary steps, C is an intermediate, okay? It's created in the middle of the reaction and then consumed in the middle of the reaction. Same with E. It's created during the reaction and consumed during the reaction. So you need to be able to identify intermediates. There are also occasionally catalysts. It can get confusing distinguishing between catalysts and intermediates, so be careful. A catalyst is present in the beginning, but it's also present at the very end. So if you don't pay close attention and you simply add these elementary steps together, the catalysts and intermediates will both cancel out and you might not have distinguished them. So notice again that B is a catalyst because it's here in the very beginning and it's here at the very end. All right, so a couple more vocab words. We talked about elementary steps. There's something called molecularity, which you can talk about only when you have elementary steps. And it is literally the number of molecules in that particular elementary step. So look down here on the table. For the first elementary reaction, there is only one reactant, so it's called unimolecular. And the one below that, there are two reactants, even though they're the same thing. There are two substances, so it's called bimolecular. The two substances can be different, of course, that's still bimolecular. And the reason we talk about molecularity is in an elementary step, it tells us how many substances are involved in a collision to make that elementary step occur. Obviously, if there's only one substance, there's no collision. It's not going to collide by itself. But if you remember in the beginning of kinetics, we talked about the collision theory, and that was simply in order for substances to react, they must collide first. So just know these molecularities, be able to identify them. Another really, really important feature of elementary steps is that the rate of reaction, the rate law is really what I should have said, the rate law can be written directly from an elementary step. So notice in this one, we just have reactant A going to products. Do you remember the generic form of a rate law? It is that rate equals rate constant times the concentration of a reactant raised to some power. Now, for an overall reaction, that exponent can only be determined experimentally. Okay, that's for an overall reaction. But luckily, what's really cool is that for an elementary reaction, they can be determined directly from the elementary reaction. So notice from this first unimolecular reaction, the rate law is simply rate equals rate constant times the concentration of the reactant A. What is different about elementary steps is now if the rate law has an exponent like the second one, we don't have to do an experiment to determine that it's second order. If it's an elementary step, we just look at the reactants, and this superscript comes directly from how many reactants there are. So look at the term molecular one, because that's kind of, it'll make it more clear, I think. So the rate law for that term molecular elementary step is rate equals K times the concentration of the reactant, and since it would be 3A, so the coefficients only in an elementary step become the exponents. Again, the coefficients only in an elementary step become the exponent in the rate law for that elementary step. So here's a sample problem. The following two reactions are proposed as the mechanism for an overall reaction. So you're asked to do three things: write the overall balanced equation, identify the intermediates, determine the molecularity of each step, and write the rate law for each step. So that's something you should be able to do, and then that's one of the questions you have in Go Formative. So writing the overall reaction, you can either add them up like I showed you in the second slide, where you literally make a list. Oh, one of my dogs is whining, I apologize. Where you literally list all of the reactants, all right, and then arrow, and then list all of the products. Okay, and then if that's easier for you to see everything, and then cross out what's the same on both sides. And I think that's it, right? So just kind of writing this in a more simple form. Okay, 2NO2 plus Cl2. All right, but let me show you an easier way, possibly easier if it interests you. And some people simply can see what crosses out by, for example, look at chlorine. It's formed in the first step and then it's consumed in the second step. So if you have a substance that's on both sides of the arrow, it's on the left side on one step, on the right side in another, you can cross them out. And so chlorine is in fact an intermediate, okay? And it's the only one that crosses out, so then you can just add what's left down here, whichever way is easier for you. All right, and so identifying the individual elementary steps as far as their molecularity, just literally count the number of reactants. Elementary step 1 has only one reactant, so it's unimolecular. Elementary step 2 has 2 reactants, so it is bimolecular. Again, the rate laws can be written directly from the elementary steps. So the rate of elementary step 1 is K, and I just put a little subscript 1 there because every elementary step, every reaction has its own rate constant, times the concentration of the reactant, NO2Cl, which is the only reactant. The rate law for step 2, rate constant, and in this case there are 2 reactants. And that's it. So hopefully that was pretty easy for you. So another type of question you might be asked is you might be given an overall reaction and then a possible mechanism or several possible mechanisms. And you might be asked, which of the following mechanisms could be possible for the overall reaction? How would you go about answering that? Well, you have to keep in mind there are two requirements for any mechanism. And we've talked about the first one. The elementary steps in the mechanism must add up to give the overall reaction. We've done that. But the second requirement, which can be a little trickier, is that the rate law of the slowest step in the mechanism must exactly match the experimentally determined rate law for the entire reaction. So let's take a look how we go about handling requirement number 2. The most important thing to remember is that you can write a rate law directly from an elementary step. So make sure that you know how to do that. Now, the other piece of information you need to finish this requirement number 2 is you must know which of these elementary steps is the slowest one. So you have to be told. That's not something you can figure out. Because the slowest elementary step is going to determine the rate of the reaction. So just to kind of give you a visual, I like to think of a relay race too. Look at the size of the funnel, the first funnel that all these go through. This funnel is much slower, so this rate is going to be the slowest of these three. And because of that, the overall rate of the reaction for number 1 is going to be slower. It really doesn't matter how fast the second step is, because step 1 is the bottleneck. And it's the same thing for a chemical reaction. If a reaction profile is drawn out, energy profile, and if it's drawn out in enough detail, every single elementary step will have its own peak. And remember what activation energy is, the distance between the reactant and the top of the energy curve. So every elementary step has its own activation energy. So for step 2 here, the activation energy starts from the intermediate. That's what the beginning reactant is, and goes up again to the highest point. So that's the activation energy for step 2. It's much higher than step 1, which means it is the slowest step, which also means step 2 is the rate determining step. So if you're not outright told what is the slowest step, but you're given an energy profile, you want to look for the largest activation energy, and that is the slowest step. Here's a sample problem just to see if you kind of got what I've been saying, trying to say. So which step is rate determining in this particular reaction? Hopefully, you said step A because it has the highest activation energy. It's the slowest. And let's look at the next question. Is the overall reaction, just make sure you haven't forgot what we learned at the beginning of the chapter, is the overall reaction exergonic? In other words, does the free energy change negative, or is it endergonic? Is the free energy change positive? So notice that free energy is on our y-axis here. And I hope you said that it's B, endergonic. Now, just to kind of remind you, when you're talking about the overall free energy or overall enthalpy of a reaction, you're looking not at the activation energy, you're looking at the difference in energy between reactants and products, original reactants and final products. And since the products are higher energy than the reactants, okay, and because to get delta G, it's always products minus reactants, if that helps you remember it all. And so that's going to give you, this is going to give you a positive delta G, which is endergonic. All right, here's another question just to kind of test your knowledge. here's a proposed mechanism. If I asked you, this is a really easy question, so if you're not sure about it, you may want to go back and listen to part of the lecture again. What is the rate law for the overall reaction represented by this mechanism? All you care about is finding the slow step, okay? And then that is the rate determining step. That's what determines the rate law. And now you can write the rate law directly from the slow step. So its rate equals its rate constant times the concentration of each of the reactants in that slow step. They both have a coefficient of 1 in front of them, right? So we just are understood to have exponents of 1. And that is it. So the correct answer would simply be A here. All right, here's one more question. Just kind of the same question, but stated backwards. If this is the overall reaction, and this is the experimentally determined rate law, so let's just imagine they found it from, let's say, the method of initial rates or something. So they know that this is the overall rate law for this overall reaction. That being the case, which of these two steps, given in the mechanism below, would have to be the slowest step or the rate determining step? Well, what you might be able to just glance and tell, but let me walk through for those of us who might not be able to. So what I do is I write the rate law for each elementary step and I see which one matches. So the rate law for step 1 would look like this, and the rate law for step 2 would look like this. Okay, so which of these two matches what they gave us? The first one. All right, so that means that that is the slow step or the rate determining step, saying the same thing. Alrighty, so these are just a couple of examples which, particularly the CLUE curriculum, likes to talk about some organic reactions, so it's just kind of exposure to an organic reaction. You can recognize it, but it's applying the same principles we've just learned in this PowerPoint. This particular type of reaction is called a nucleophilic substitution. A nucleophile is simply something that has an electron pair that it donates to some electron-poor site. And so we've talked about bases. Most bases can act as a nucleophile too. So it's that lone pair of electrons that make it a good nucleophile. All right, so, and again, most bases can act as a nucleophile. We know hydroxide's a base. And if we were to draw the Lewis structure of hydroxide, it would have 3 lone pairs of electrons. So it can certainly serve as a nucleophile. And then what nucleophiles do is they tend to be attracted, because they're electron rich, they tend to be attracted to electron-poor sites. And so just drawing out this compound, the Lewis structure, we know that bromine is electronegative, so I'm going to give it a partial negative charge. We know as a result of that, the carbon is electropositive because bromine's draining off the electrons, the shared electrons. And so because carbon is electropositive, it's somewhat electron deficient, which means our electron-rich nucleophile is attracted. So remember our curved arrow mechanisms? We can show a curved arrow starting with one of the lone pairs on the hydroxide, and it's going to make a bond with the electron deficient carbon in methyl bromide. And because carbon can only have 4 bonds, right? And this would be 5, it has to kick something out. So it kicks the bond between carbon and bromine breaks, and it kicks bromine out. And the bottom line is the hydroxide has replaced the bromine. And so anyway, I won't go into that mechanism much more, but that could be a bonus type question on your next test. And it's just, if you're going on to organic, you're going to see a bunch of that. All right, so which species must be present in the rate determining step? How do you answer something like that? So you may want to turn off the video for just a minute, see if you can figure that out. And if not, I'll walk you through. Well, you always look at the rate law, or if you're given elementary steps, look at those. That's where you're going to find your clue for the rate determining step. Now, if a step is rate determining, that means that its reactants in that step are important to the rate of the reaction. All right, so look at the rate of the reaction. What are the species that affect the rate of reaction? Methyl bromide and hydroxide, both of them. Okay, and since they're both in the rate equation, that means they are both in the rate determining step. If an ingredient, if a substance is not in the rate determining step, it is not going to show up in the rate law. All right, so we're getting close to being done. This is showing you a little bit more neatly than I did on the last slide, the mechanism of the previous reaction. So again, your curved arrow mechanistic arrow is going to start from the lone pair, a lone pair on the hydroxide. It always points to the atom that it's creating a bond with, which is the electron deficient, in this case, carbon. And the second curved arrow shows that, remember our curved arrows show bonds being made and broken? The second curved arrow shows the carbon, my dog is making me wiggle. All right, shows the carbon-bromine bond breaking. So here's your new product. And here's the rate law they gave us. And here is the energy profile. And a final word, and then we're done with this PowerPoint. Catalysts. We talked about those in the beginning of the PowerPoint, that they are a substance that are present in the very beginning of a reaction as one of the reactants. And they're also present at the very end. And that's because catalysts, although they're important to a reaction, to the rate of reaction, they do not get consumed, okay? Catalysts do not get consumed. They show up in the beginning and in the end. All right, so how do catalysts speed up a reaction? And by the way, they speed up the forward and reverse reaction, okay? So they don't affect equilibrium, which we'll get to in the next chapter. They speed up a reaction simply by lowering the activation energy of the reactant. And they do that by providing a new pathway. And I always like to give the example of, if you have a mountain and you need to get to the other side of the mountain, you can either go over the mountain, or if somebody has drilled a tunnel through the mountain, you could walk through the tunnel, okay? So you could think of the tunnel at the bottom base of the mountain as the catalyst, okay? It's allowed a new mechanism to get to the same end result. Catalysts that we use a lot, well, organic chemists do anyway, and they're used in industry quite a bit too, is when we want to take a hydrocarbon with a double or triple bond, and that's called an alkene. That's just a little bit of organic knowledge. And we want to turn it into a hydrocarbon with all single bonds, which is called an alkane. So only the ending changes. And we do that by adding hydrogen across the double bond. But that reaction can be sped up tremendously simply by adding a metal such as platinum as a catalyst. And how that works, although platinum doesn't really participate in the nitty-gritty mechanism, what platinum does is it attracts the reactants in the reaction to it. It has a great amount of surface area, And so both the alkene and the hydrogen gas are both attracted to the platinum, so they're in closer proximity to each other than they would be if the platinum wasn't there. And so in that case, platinum serves as a good catalyst. That is it for this lecture. Make sure you answer the Go Formative questions.